welcome. Happy to see you. And it's a great pleasure to have you as Professor Simon CRM Professor. I have to say that Javier de Lucas has international standing. His career started in 2004. He did a master, next PhD in 2009, and doctorate d'etat in 2012, habilitation in 2017, and become a professor at the Warsaw University in the institute that is called Institute Cathedra of Mathematical Methods in Physics in 2022. So I'm very glad to have you and welcome for your presentation. His field is the classification of finite-dimensional Lie algebras for system of partial differential equations.
Well, so thank you very much. It's a real pleasure to be here and to hold a Simon Syrian professorship till the end of the year. It will be a pleasure to talk to you, to discuss scientifically or not. So it's not my first time in Montreal. I've been for much shorter stays in here a couple of times. And I'm really happy to be here again and to work for the following months with you. So I wanted to present part of my research, to introduce myself, say what I am, about what I'm doing research. I have kind of lots of fields of research, and everything is contained in differential geometry, differential equations, and integrable systems, application of integrable systems. We can mention all my research in these fields, that they are quite large. As a PhD, I studied first of the differential equations, admitting what is called a superposition rule. That it is a method to obtain the general solution of first of the differential equations in terms of particular solutions and some constants. This was a very well-known topic in this place, in this area. Jean has works about it. Winter had lots of works about it. It made this topic famous. Veronique Hussein, and there are a lot of people about it, doing things about it. After that, I moved into differential geometry, more differential geometry topics. I was doing the same as I did before, but I was studying symplectic geometry, Poisson geometry, multi-symplectic geometry, class-symplectic geometry, topics about Lie algebras of vector fields. And lately, I do things about numeric stuff, about stochastic differential equations, about very pure differential geometry, double theorems, things about infinite-dimensional manifolds, applications in quantum mechanics, classical physics, lots of things. I don't pretend to describe everything I do here. I just want to make that kind of fast introduction. As I said, differential geometry, differential equations, integrable systems. If it can be containing one of the things, is quite probably I can say or do something about it. Today, I decided to describe one topic, and my research is devoted to, as I said, it's some topic that is very related to the Syrian, so many researches in here. Maybe it was a long time ago when this was quite famous, things like that. But I think that it can be interesting, and there are many things to be done. And well, I can say that when I did this, well, it was published in very good journals, like geometry, and people got interested. So I thought that's very interesting here. So let us how this works. What I have to point to, or this day. How it was. Okay. This. Okay. So my talk today is about three different things. Yes. So first of all, I will talk about the classification of finite-dimensional Lie algebras of vectors. I will explain more or less how it looks like and where this topic can be applied to. Okay, why is this important, interesting? And I will show you some of my results. Okay, some of them can be quite interesting, and some of them concern my actual research, what I'm doing here now. Then I will talk about Casimir tensor fields. These Casimir tensor fields are a geometric generalization of the Casimir functions, maybe you know. Okay? They work in a similar way, but they are used for more things, let us say this way. For example, to turn in a dynamical system to a Hamiltonian system, for example, with respect to a symplectic structure, Poisson structure, other things. It can be understood as a generalization of Casimir functions. And finally, using these two things, I will introduce Lie algebras, finite-dimensional Lie algebras, Hamiltonian vector field. I will classify them. I will say which are, okay, the shape they have and where they appear, the applications they have. Okay, so the motivation of all this work came as many other things related to Lie algebras opposed to Lie. So if you don't know, the initial motivation by Lie was due to Galois. Galois studied the symmetries of polynomials, that means the evaluation of the symmetries of the polynomials, was able to classify when we can obtain the roots of a polynomial in terms of elementary operations. So they said, oh, can I do such a thing for differential equations? And what he did was to develop a theory about continuous group of transformations that map solutions into solution of differential equations. Okay? If you have infinitesimal continuous group, is another part related to it, you will get what now are called Lie algebras of vector fields. Okay? The continuous part is what gave rise to Lie groups, actions in the literature. Okay, and another thing that is very specific, but as I said, it was something that was developed mainly here, apart from Lie, is about this Lie system. There are systems of differential equations, or first order differential equations, non-autonomous, whose solution can be written as a function as a particular solution. Like in analysis, third year linear system of differential equations with time-dependent coefficients. Okay, the linear solution is a linear combination of something of the sort. Okay, so it was something he wrote. But at the time, it wasn't the most important thing, but afterwards, many people got interested in it. So this is kind of what I'm going to say, something that people don't used to know is about that Lie had great ideas, really, really great ideas. At the very end, many of the things you can study, you can find them in his works. Of course, you will find it in French or in German, of course, and in words that they are not normally available. But you can find it there. But there are some problems with Lie. It's not normally known that Lie had problems to communicate his results. It was difficult to him, and he got nervous because he did things. He thought that everything done by many other people could be understood in an easier way. I don't want to. Okay, at least at his time. Okay, in many of it. And it will be a little about it. In part, this is due to the fact that when you read Lie's work, it's obscure. Sometimes he doesn't explain everything he does, and give problems. Okay, and it's a little bit of mess. Normally, students wrote these works, indeed, or they helped him to do so. So one of the things Lie did, and this is what today is going to be my research on, is the classification of Lie algebras of vectors. So what Lie did? Classify the algebras of vector fields on R. He did it on C. He did it also on C2. By means of a very interesting trick, he did it on R2. And then he said, but he didn't publish, that he classified all finite-dimensional algebras of vector fields on C3. Okay? He wrote just a couple of them. It's something like 60, 80 pages long classification. Okay? Difficult to understand in German. There is no translation and it's hard, but one can manage. Indeed, I'm doing this now. So, in this work, there were several technical assumptions. In that time, and in many cases, these technical assumptions are not relevant. But if you want to study, for example, stability of dynamical systems of differential equations, they do. So the classification needed for certain topics is unfortunately useless. But for most of the things you can do, it's great. Okay, so for many things, they are perfect. For other ones, it's not. They are not. So the final thing is that his proofs contain unclear statements. And the unclear statement is not about that you read it and you say, come on, I don't understand it. Okay, doesn't matter, maybe it works. It's about some guy, some research, serious research, reading it, committing mistakes, writing papers, and with all the paper, copying your results and saying things that are wrong again and again and again. Okay, and this had to be solved, and this was solved for people from Montreal, okay, in several cases. So I will show you some proposition by Lie in 1980. Yeah, he said every finite-dimensional algebra vector field on R is locally diffeomorphic around a point where one of its vector fields does not vanish to a least algebra of this. You have three vector fields. Okay, you can look at the bracket of this vector field. We are reading it here. Sorry. Okay.
What is it? Talk about the local diffeomorphism. How do you? What is the topology in that?
It's not over for now. I mean, you have nothing. You have as a manifold is the standard one you have for now. Okay, there is nothing weird. It's everything is more or less standard with manifolds. There is nothing special. If you try to do such a thing, there is more even to say. Okay, this is about normally smooth functions. Okay.
So do you consider non-singular vector fields or do you allow singularities?
The thing is that for Lie, all these vector fields are smooth. Is what he did, and additionally,
No singularity.
no singularity. Yeah. And the thing is that there is another thing he did, but sometimes people don't use it too much. What they say about it. These algebras are classified when at each point of the real line, when you are saying that locally diffeomorphic, one of the vector fields might be different from zero. Okay, if you pick up an algebra of vector fields, and it happens that at one point all the vector fields of the algebra are different from zero. Okay, it has happened in the example I wrote. Then the result idea is not true. I mean, he said you have a algebra vector fields on the real line. Okay. And at certain points, one of the vector fields different from zero. Yeah. So there is a change of variables that maps this algebra into subcase as well algebra of this. So no singularities, okay? And at the very point, there is at least one vector field. Why? Because the proof is that you pick up one vector field that does not vanish, you put it, you rectify it, you look for coordinates in which the vector field will be partial with respect to a variable. And then you consider that this vector field acts on the algebra, on the whole algebra. You complexify this thing, you say that there is a eigenvalue, and you start studying the possibilities, okay, algebraic, and then you go back to the real case. Okay, this is the idea. But the first step, one of the vector fields must be different from zero because you have to rectify it. If you don't do it,
Zero everywhere or you
one point. At one point, must be. It's not in one point. Okay. If not, what happens is something like I wrote in here. Yeah. For example, as I told you, he said that everything must be of this type. Okay. This is S of 3, 2 times 2 matrices real traceless. Okay. The algebra of this vector of this matrix is morphic to that. But you can construct any other things. For example, if Fi are pump functions, like I wrote in here, okay, you can write them in such a way that when one becomes zero, the other one is not, okay? And these points, if you can see that in these points, these pump functions are going to be smooth, but they are not going to be analytical, okay? It happens that the vector fields of this set commutes between themselves. Okay? Then you have an R2. The algebra, commutative, and there is no way to obtain a commutative subalgebra. There is no such a thing. So you see, you can break this. Also, you have just a single vector field with a zero, okay, and you want to say that okay, this spans a one-dimensional algebra, like this one vector field, and you want to put it in one of these to find a change of variables that will map this vector field into this. When you make an arbitrary change of variables and you fix with a loss of generality that at x equal to 0, the new variable is equal to 0, this is the same vector field, the new variables, but this expression, Taylor expansion, okay, it will be different from zero only on the k term. So that means that no matter what you will do at the zero, this thing, the Taylor expression at zero, it will start to k. If k is bigger than 2, it will never be of this kind. Okay, so you cannot do it. So the thing is that these problems appear when you are talking about the stability of vector fields on the real line, C2 on R2 or whatever. So if you talk about the stability, pick up this classification and straightforward to the okay. That's what, well, not exactly. Yeah, that's it's
So go back to that.
Yeah.
If I put x1 and x2 equals 0, that
X,
algebra
which one?
is inconsistent.
One?
You have this algebra there. Yeah.
This
Above-
one?
No, above.
This one?
Above.
Above? Yeah.
Yeah, below that.
Below this
That.
one. Yeah.
If I put x1, x2 equals 0, it's inconsistent at first glance.
It's but yeah, like equal to zero. I don't understand that point.
Well, you said 1 is not 0, so suppose 2 are 0.
I mean, at every point, okay, so there is always one vector field that is different from zero. Yeah.
Yeah, so
Yes.
at one point you have one vector field is non-zero and the other two are 0.
In this case, not it's not needed to say. I mean,
So if I take little x equals 0. then-
x equal to zero.
Yeah, then big X1 and big X2 are 0.
This one is equal to zero, and you have still one. Yeah.
Right, but look at the first commutator, makes no sense.
No, this is Lie bracket.
Of a vector at a point has to be vector field.
Yeah, I mean, this thing is the Lie bracket of vector fields. It has no sense to make it at a point. And then this is just that this is a Lie algebra vector field, okay? That's another stuff that's going on. Okay, thank you. So there is one interesting thing. It is that if you start by means of a certain differential equation of this sort, and you put these vector fields, okay? If it turns out that these vector fields span finite-dimensional Lie algebra vector fields, the thing that Lie said was that there will be a change of variables such a way that this vector field will be free and they will be of the sort given before. Okay, so you get something like this. And this is called a Riccati equation or a linear one in this case. So this was done by Olver and Königsberger. It was proved by them that if a differential equation of the real line time dependent that's the superposition rule, I mean the general solution will be a function of a certain set. So the parameters must be this way. Lie got annoyed, strongly annoyed by this thing, because he took a look at this and said, come on guys, I did this 13 years ago. What you did for the last 10 years, because this is the last result after 10 years of the 3-4 people doing this. If you apply my theorem, my theory, this is trivial. So you publish a paper, 1893, you say this is a nice result. 40 papers after that, is Lie saying that your result is absolutely trivial, this is a particular case, I will do it much better than you. And in the same day, he published another paper, even the Lie theorem characterized and all this stuff. But, as I told you, they have problems about explaining his results. And this was written by Artermio Gonzalez-Lopez, I think that the Universidad Autónoma from Madrid, Kamran, maybe it's Mankiel, yeah, I don't remember, and Olver, yeah. It was written, these results, their paper, will help clear up some confusing and contradictory statements in the literature of this problem, I mean the classification. Blah, 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 blah. More or less, Lie did it wrong, it was not clear, people starting copying the results, saying things that they are wrong, where we are going to put it right. So that's what they did, okay? And that's why people used to call this the GKO classification. It's the same, Lie did, but probably. And differential geometry language, modern. Okay, it's pretty much clear. It's a very nice work, in my opinion. There are many things done and many things to do. So it's kind of okay, the things to understand. So another problem by Lie was the following thing. Okay, it was related to my research while I've been a PhD. So it was that geometrically, when you have a system of differential equations of this type, you can construct a time-dependent vector field. Okay, yes. Locally, these things, the coefficient will be something like that. T is a parameter, time-dependent vector field just means that for every value of T, you have a vector field, okay? So it's nothing, you can define this more geometrically, but it's not like that. This can be to prove, you can prove that it is well-defined everywhere, that everything works out, and so on. So when you have, when I will talk about these systems, I will talk about time-dependent vector fields because the ratio is 1-to-1. Okay, this is geometrical, it's more useful. So the thing is that a superposition rule for a system, I mean, one of these things, one system differential equations, is a function that depends on n things, that there are particular solutions, and a point of your manifold as initial condition, and by means of n fixed generic solutions and 30 parameters, you obtain the general solution. Okay. For numerical methods, it's very useful. One techniques have lots of results, blah blah blah. Which is very, very interesting. Sophus theorem, Lie proved that if you have a system, something like this, and has superposition rule, is a linear combination with time-dependent functions of vector fields that close a Lie algebra, finite-dimensional Lie algebra. Lie says that in a paper by himself that this is the theorem about explaining the superposition rule is this. Sophus was some kind of student, I wrote it over there. Okay. People call this system Lie-Sophus system sometimes. It is fun because Sophus did this, copied mainly Lie's result, and he never did anything. Yeah, his name still. What is wrong? Well, the thing is that Lie theorem by Lie is problematic. You read it, you say, this I don't understand it, this I don't understand it, this I don't understand it, but the finals of this, right? Yeah. So, okay. So people started copying this, and Karinian and Grabowski-Marcus said there are some gaps. Gaps means that there are parts that they are not explained. By Simpson, Lie, and all this. Okay. So they speed up the gaps and prove everything. There was some conditions to be satisfied. They are not in Lie, at least my German is not that good, but well, I tried to read it, I didn't find it, so Lie somehow maybe had another idea. The result is true, but the proof is missing set techniques. Okay. So let me explain you now about the classification made by Kamran, Olver, and Artermio. What they did, okay, and what is the final result, and what I did after them. Okay, so I will explain a couple of technical things, the minimal ones to understand what is going on, which are the problems of this classification, and how to deal with it and to do stuff, interesting stuff. So let us start by having a Lie algebra vector fields B on a manifold N. And normally, to do all this stuff to classify, you define something called associated distribution. That means that for every point of your manifold, okay, you will attach to the point a subspace spanned by the vector fields of the Lie algebra. This distribution can be shown to be involutive and integrable. Okay, involutive vector fields take value in here. This thing for each point. The Lie bracket will belong to this distribution, will take values in the distribution. Okay, it's integrable for each point of the manifold N. There is always some submanifold whose spanning space is at each point with the distribution at that point. Okay, but this distribution is not regular. That means that these spaces they may have different dimensions. Okay. Many of these things, these result definitions, they are in Lie, okay, but they are a little bit chaotic, as I said. It's something written in the 19th century, so most of the things you probably know from school, they weren't in that time. So they were not manifolds. The standard manifold definition was the 1920s. So you know what we are talking about. And the thing is that when you have a Lie algebra vector fields, a regular point of the Lie algebra is a point that satisfies that you pick up the distribution of the Lie algebra, it will be regular, locally regular. These spaces around that point locally, they will have all the same dimension. If it's not true, the point is called to be singular. The An easy example for that, talk. Is there any something to it's no.
Are there regular?
Okay, anyhow, that it doesn't matter. Maybe I can go with it. For example, imagine you have a vector field, okay? And the vector field has an isolated pseudo, yeah, only what it bounces. So the vector field by itself spans a Lie algebra dimension one, yeah. And that point where the vector field balances, okay, the distribution, the value of this subspace is 0. But that point is isolated. Okay, around it, you have points where it has no values. So at that point, this will be different from 0, and the distribution will have rank 1. So what it happens that in those points, the distribution will be not at those points, the distribution would be singular. It will be singular points. Okay. So say if you have, for example, this vector field, yeah, on R, you have the 0. This 0 here will be the value of x is 0. The Lie algebra span like this because they fixed, yeah. Now it goes to our this vector field times a constant. So at 0, all the things that, well, let's just say right here, would be 0. Okay, so the distribution in here, this is just 0. But at any other point, this would be different from 0. So this thing, the dimension of this would be 1. So this is a singular point.
I think you're using the word distribution slightly wrong directionally, because distributions by definition are constant rank.
Yeah, I mean, John, the problem is that it depends on what you are working on. For most of the people, maybe you are right. I mean, when you talk about
just think
the distributions normally, the thing is that this thing I call as a distribution normally is called an associated Stefan Sussman distribution or an associated generalized distribution. This is the normal stuff. But you know, when you work on a field where everything all the time the distribution is generalized to Stefan Sussman, at the very end everyone says, okay, drop it and don't tell it. But it is true, yeah. Many cases, as John says, when you define distributions, you define it to be regular. Okay, but if you are working all the time with Lie group actions and things like that, normal stuff is
which doesn't mean that it's regular. No. Is it Frobenius gives you the regularity condition. The fact that it's regular is something more, because that means that the leaves are embedded submanifolds, and you can have an integrable distribution whose foliation does not consist of embedded submanifolds.
I mean, about that, let us say it this way. Okay, I know that. Okay, I know, for example, that all Frobenius theorems for generalizes Stefan Sussman analytical vector fields, smooth vector fields for distribution and things like that. So depending on your definition, what you want to say, okay, these properties about this inverse submanifolds and things like that are true or not. The problem is about, as I said, about what is your definition and according to which are your theorems. For example, if you have this generalized distribution, Stefan Sussman, normally, in some sense, regularly means that the rank is always the same. Okay, if it's always
okay. Take a torus and take an irrational slope constant vector field. That's an integral distribution, but it's and so
it's really not that it's not that true. Yeah,
but the leaves are dense. There's one leaf which is dense. So that's not a regular man. That's not an embedded.
I mean,
that's not a regular.
Yeah, but I mean, as I told you, it depends on. You can define integrable. Integrable is, I think, what you are talking about regular. In your case, my definition of integrability means that for your vector field and theorems where the relation between the two vector fields is something that is irrational. Yeah, what it means. In my case, in my definition of integrability means that at one point you pick out your vector field and there is some summative H point that is standard. If this summative is such that it fills up densely of the torus or not, is something that we don't care about. You can do it, okay, but this is another thing, okay?
But that's a perfectly good example of an integrable distribution according to Frobenius and all the standard textbooks.
Yeah.
Where there's a maximal integral manifold, but space filling. It's not a regular, so it's not an embedded submanifold. It's not a foliation by embedded submanifold. So that's what I would call it.
Yeah, I know, but you know, your example is a thing, by definition you say, take it locally. It was that. But it's another way, okay? This example, I know it because I done this on the first year, yeah? About this thing. But as you saw, it's a matter of definition of what you want to understand as regular, not regular. So, the thing is, from this point of view, everything is local. So the facts about this is defined on the whole space. There is one leaf filling up the one manifold. It has nothing to be to take care of it. Okay. So the thing is that, as I said, there are two on the R2. There are two types of locally around generic points of the distribution. There are the ones that are called primitive and the ones that are called imprimitive. Imprimitive means that there is a rank one distribution, regular one. I don't know how to say now. Regular rank one distribution that is invariant by the vector fields of the elements of the Lie algebra. If not, it is called primitive. Okay. Why is this important? Because when you classify all Lie algebras, finite-dimensional Lie algebras of vector fields on the plane, it turns out that the properties of the primitive and the imprimitive are absolutely different, and they are related to different structures, complex and real ones. So normally, when you describe them, you do it by saying that you have 8 classes of primitive Lie algebras. I mean that you don't have this one rank regular distribution. We say everything about property. Invariant under these vector fields, you have 8 classes, and these 8 classes, some of them they may have parameters. Okay. The other thing you have to take into account is that here, what is written is that these Lie algebras of vector fields, they are isomorphic algebraically to these Lie algebras. Okay. This is called the domain. This is those regular points of this Lie algebra. This is something that you can work on this. And you have this nice thing. Oh, sorry, now it works. The primitive ones, and there are lots of them. Okay, you have 20 classes. Okay, this classification is made, as I said, only for Lie algebras at points that are regular. Okay, if you move away from them, this does not work. And you have lots. And one of the important things that they are parameterized sometimes by 13 parameters are alpha, even for functions. Okay, so there are lots. The other thing you have to take into account is that you can have isomorphic Lie algebras of vector fields algebraically, which are not diffeomorphic, like these resources. So if you are doing something and you have a certain Lie algebra of vector field, you say, I know the algebraic structure because this is, you make commutators and you can work it out. You don't really know many cases which of these classifications is, and this is very difficult to know because before my works to guess which one is it, you could need to find the change of values to matter to it. And this is difficult because are PDs, and you will have to solve if a system of PDs have solution. And this is always difficult and tricky. So this is what it was done. And now from all these, well, I studied all these algebras of vector fields a long time ago. My results were published in Journal Differential Equations in 2015 and 2017. And I just, I studied which of these algebras of vector fields are Hamiltonian with respect to a symplectic structure. But you can imagine 28 families with parameters is crazy. If you try to look for a symplectic form turning these vector fields by means into Hamiltonian vector fields, you want.
I'm sorry, is it an R2 or C2?
R2.
R2. And you're saying for some symplectic, not the standard symplectic structure, but some
whatever. The one. whatever. Everything here is up to diffeomorphic. When you say that these the algebras, you have the classification, it means that this is one diffeomorphic. You have to find some, okay? Some of them. So if you want to look for this symplectic form normally, you will have to make the derivative of a generic symplectic forms in terms of the all vectors of each family, and to check out if you have solutions. But before that, I studied the structure of this. The first thing was something that was known by Lie already, and it was also stressed by Kamran, Olver, and Artermio, was that there are some relations between these vector fields. I mean, these Lie algebras. Some of these Lie algebras, they are diffeomorphic to these algebras of other Lie algebras of the classification. They are related between them. The thing is, what it was known, it was that this is a maximal one, P7, and I11 were maximal for 30 classes of vector fields being conformal with respect to certain flat metrics. This was what this was done. But take a look at this diagram. The thing I want to explain is, you know, there are 28 classes, yeah? It's kind of big. Look at the relations between them. These arrows are saying whether one of the Lie algebras is diffeomorphic to a subalgebra of another one. And you will notice that this one is not included in any other one. This one is not included in any other one. This one is not included in any other one. And this one is not included in any other one. They are maximum, okay? And all the remaining ones go here, 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 here. So your 28 classes of Lie algebras of vector fields really can be reduced to 4. This, and this. And what I prove is that you can characterize these things. Well, this one, this one, this one, and this one. Well, this is a conjecture. In reality, there is something missing there. So, geometrically, if on the plane you have a flat Riemannian metric, and you look for conformal Lie algebra conformal vector fields, it is finite-dimensional, I prove that it will be diffeomorphic to this, or a subalgebra of this. If it is hyperbolic, it will be this. If it is projective, if you have projective vector fields for a metric, flat Riemannian metric, projective means that the flow of these vector fields map geodesic into geodesics, okay? Not respecting that one parameter, but something like that. You will get this. This is what's new. And you will get this. But this is a conjecture. This is for this. The problem with this I20 is that I couldn't finish the thing. So I never wrote it as a theorem. There are several cases left. But you know, this is quite big. This parameter can be whatever. So it was difficult to me. And the condition, the differential geometric condition local to check out whether they are projective or not, it's quite complicated. So
what are the dimensions of the board?
The dimension of
The dimension of the algebra.
The dimension, this is not fixed, can be whatever. I mean,
So it's not one algebra.
I mean, you have, for example, this one, this is 8. Okay, this P8 is maximal. This one is 6, yeah, 7. The other maximal.
Okay, so you listed what the algebra.
Yeah.
But you've listed 8 there, right? Not 4.
I mean, this is not the primitive. I said all this classification wrong. All this thing can be divided into primitive and primitive. This is related to some Lie's result, okay? They are all, any Lie finite-dimensional Lie algebra vector fields must be here. But then, between them, there are filter relations. Some of them, they are including others, okay? They are, for example, like here, P4, okay, is locally diffeomorphic to a subalgebra of P6, and these are the relations.
So if you allow it to be in primitive, you have the algebras of arbitrary dimension.
Yeah.
Realized into
two, yeah. It's huge, really huge. So, I mean, it's as easy as taking this and making it complicated. You will notice that this thing can be whatever. So the problem, the big guy is this one, and this is the most difficult one to trace. But seems that it should be answered. So you have 28 classes. People say this is very crazy. This is a lot of work. There are a lot of the algebra. The classification is difficult. What I am telling you is that projective conjecture, okay? All the algebras of vector fields on R2 are finite-dimensional algebras of vector fields on R2. They are diffeomorphic subalgebras of projective vector fields of a flat Riemann metric field, of a flat hyperbolic metric. All they are conformal with respect to flat metrics. I try to do this for R3 because they are partial results, and so far so good, it works, but I'm not sure. Okay,
These are not requirement to be Hamiltonian.
no, this is the part. This is general. This is part of this result. Okay, this is P7, the things that I go to it, and then this is I11. These are the subfamilies I go to it. Okay, there are two maximal, and I didn't do it for pH. E20 is a lot. Is a huge thing.
Is the conjecture for globally diffeomorphic or
Local diffeomorphic with all these assumptions you have to do it. If you remove the assumption, you have to start from the beginning. Okay, and it's important because, for example, the stability of systems on Arch, yeah, we have linear vector fields. They have a singular point at the beginning. It doesn't work. Okay, it's a singular point.
oh no, you're admitting
Yeah, you don't need to go to weird things. I mean, it really happens frequently. I mean, if for general physical system, you go to a point, you consider local things, you don't care much about it. But in stability, you go to the point where the problems arise. So it's okay. We have 20 minutes, more or less. I will finish it before that. I will explain something about this classification. That's the Casimir, the so-called Casimir tensor field. Okay, this can be a little bit tricky, but I will try to explain. So imagine that you have a finite-dimensional algebra of vector fields on R2, and that it is morphic to SR2. Okay, so I told you, you can have different Lie algebras of vector field that they are algebraically isomorphic, but they are not diffeomorphic. There is no change of variables, maybe one, two. So you have 4 of them. You go to the GKO classification, Lie classification, if you want to say it this way, and you have 4 options. You have your Lie algebra, you have 4 of them, and you say, okay, which one is it? Yeah. The typical stuff, change of variables. You write that it must be a change of variable, mapping one to another, and you have the problem that you don't know even how to start. Yeah. You have a basis of 1, the second one will have the same constant structure, but you will have a PDA and you don't have no idea if there is a solution. So normally you will be stuck. Okay. So what is the trick? The trick is the following one. It's a little bit algebraic, that you will say. The thing is that what I'm going to do is to construct an invariant for each one of them. Okay, something that it will be geometric, because I know that algebraic structure doesn't work because it doesn't classify. They are all isomorphic, so it must be something geometric. But I will use the algebraic structure to construct the invariant. This is the funny thing. So, okay, consider this as G. What is this? G is a Lie algebra. You have the elements of the Lie algebra, and there is something called the symmetric algebra of polynomials. You consider elements of the Lie algebra like numbers, and you can multiply them, essentially. Yeah? And you consider that the multiplication is commutative. They behave like variables. Okay, let's say that's right. Indeed, when you have a Lie algebra and you have the dual one, a basis of the dual are linear functions. Okay, and essentially you have the same number, independent number, like the Lie algebra. So when you have these things, okay, you can multiply them because they are functions, and you obtain a third type algebra of polynomial functions of these linear elements of the dual. Yeah. So essentially, you can use this stuff to introduce here constructing. When you have the elements of G, you can consider that they are linear functions of the dual. Okay, this is a funny thing. So you can multiply these linear functions and you will obtain polynomials. Okay, and it turns out that the dual of a Lie algebra has a Poisson structure that maps the polynomials into polynomials. So these things, these linear functions of the dual, can be considered as functions on G star, and this thing here maps things of these polynomials into polynomials. So this thing that is a Poisson bracket acting on this gives you a Poisson bracket. You have this nice structure, okay, and it gives you a certain Poisson algebra of functions, so polynomial functions. So the thing is that when you have SL2, okay, you can consider the dual linear function multiplied of 10 polynomials of degree 2. Okay, and you can consider, yes, the Poisson bracket I told you before. Yeah, and then you can define a mapping, and this mapping goes from these things, these functions, into tensor fields. It is easy for real element, linear element of, well, for every element of the Lie algebra, you map just one of the vector fields of the Lie algebra. You have your Lie algebra, okay, vector field, the abstract Lie algebra. You pick up a basis of the Lie algebra of vector fields that has the same constant structure of the abstract one, and you put this into one to them. When you do this, and here you have something that is a Casimir function, something that commutes with respect to this Poisson bracket with everything. Okay, and this can be worked out, and lots of words about it. It can be worked out algebraically. This thing in here is a tensor field, and it is invariant with respect to the Lie bracket of all the elements of the Schur-Kubel Lie algebra. So out of something algebraic that is invariant due to the constant structure of the algebra, you have constructed something geometrical. Okay, two control variables. If you write this in a basis and you obtain the determinant of the matrix of this thing, you will obtain a number, and this is an invariant. So, just an example, okay? E3, you have this. I started by this, yeah? This thing, these three vector fields. You know that a Casimir function for this thing that it was isomorphic to SL2, it was B1, B3, what is this? Okay. Well, the Lie algebra, this is a Casimir function. Yeah. So if instead of this, you put x1, x3, x3, x1, and this twice this, it turns out that this is invariant with respect to the Lie bracket with x1, x2, x3. And you, when you map this thing into this thing, okay, you obtain 0, a constant. Okay. So it only happens this for E3. If you have a certain Lie algebra is equal to SL2 and you obtain this, and this goes to 0, it means that this is E3. And this is one of the theorems. Okay. This object is called a Casimir tensor field, and this can be used, for example, to work out symplectic force Riemannian metrics invariant for the algebras and vector fields. Okay. Indeed, what I did geometrically is how the Lie algebras, by means of the Lie structure and geometric things like this, you construct the symplectic structure. Okay. Okay, so let P be a Schur-Kubel Lie algebra diffeomorphic to P2, E4, and E5. I told you at the beginning that we will have 4 isomorphic to SL2. Okay. One of them, as I told you, when the Riemann invariant Casimir tensor is 0, is E3. So we have still 3. We will have to know what to do with them. So if you pick up the Casimir tensor field, okay, that is something like the image of a Casimir function, essentially. In a 13 basis, you work out the determinant in a 13 basis of this vector field and the sign of this number. Well, it's easy. Positive is P2, negative is E4, 0 is E5. And things. You don't need to change the variable. Okay, you pick up the things, you work out the invariant, it works. End of the story. This is an example of what it works out for them. This is a practical example. Okay, this was my winter. It did a long time ago. These are called mean-Lefine equations. Okay, they appear when you have an quantum harmonic oscillator with time-dependent frequency, and you want to put it time-independent, you make a change transformation to put it as a time-dependent, you have to solve certain equations. Okay? If you have, for example, oscillator with a centrifugal curve, this thing, like C has to have some, whatever. This can be associated with the algebra vector field. These commutation relations have SL2, but you have no idea which one of your classification is. So the only thing you have to do is you pick up these things, you pick up the Casimir, determine the coefficients, the sign, and it turns out that after doing all this stuff, what you obtain is C, this thing. So when it's positive, P2, negative, I4, 0, I.
Can I just ask, these Casimir tensors are always symmetric tensors?
Yeah.
So that's, I'm just trying to relate it to the usual definition, which is the center of the universal development.
Yeah, it's a realization.
You just symmetrize, you symmetrize and then reinterpret it.
In this is a part, yeah, indeed. And it's a realization. You have the, I didn't want to talk about the universal enveloping algebra, but the other thing you do is that for the universal enveloping algebra, you know that the equivalent relations between them, you can always do obtain a symmetric representative, yeah? So you map it into a tensor field and obtain it. It can be done for other the algebras and for so-called deformed universal enveloping algebras, but it's kind of technical. Well, I didn't want to get into it. So let us go for the last time of the talk. Everyone is knows symplectic geometry. Everyone, more or less. Okay, quick. A symplectic manifold is a manifold with a true differential form, which is closed, okay, and non-degenerate. Non-degenerate means that if you make the contraction with a vector field and it gives you 0, this vector field is 0. That's so a Hamiltonian vector field is one that when you contract with a symplectic form, it gives you the differential of a function, essentially. Okay. This is a Hamiltonian vector.
Is n the same as the dimension? Is little n the same as the dimension of big as big N?
Once again,
It is the little n
and this thing, okay, is here is half the dimension of n.
half the dimension.
Okay, it's well, this is I wanted to put it another way because it's boring, obviously the same. It's a symplectic form is a closed one whose when there is the exterior product with this n times, it gives you a Borel form. It's equivalent. So this is even dimensional. It's a little bit weird sometimes useful, but normally no one tests it. It was some kind of thing. Okay. So Ham and omega is the set of Hamiltonian vector fields. You can define for every function you have one unique Hamiltonian vector field. You can describe a Poisson structure. There is a nice thing that the commutator of Hamiltonian vector field with different functions, it will be minus the Hamiltonian vector field, the Poisson bracket with these two functions. Well, this I will not need it, so I will skip it. Now, a Poisson manifold, you see here that when you have symplectic form, right, you finish defining this thing, and this is a Poisson bracket. It's a Lie bracket, and it satisfies the Leibniz rule on each entry. Okay? When you fix this, it acts like a derivation of the second term, the other way around. So when you have a certain symplectic manifold, you have this Poisson bracket, okay? But you can define a manifold with a Poisson bracket in general, and normally it does not come from a symplectic manifold. It's much more general, and this is called a Poisson manifold. Because of the properties of the bracket, that is a derivation in terms of the second part and the first part, there exists a B-vector field. I guess that everyone knows this. Antisymmetric tensor product of vector fields. Okay, that describes this bracket. It will be yes, this is acting on the differential. You can understand that this is a vector field, and so another vector field minus something of the sort. You can characterize when it's a Poisson, when it's bottom bracket. Let me go a little bit fast. Okay, there are examples where these things appear. What I wanted to tell you is that I gave a few. Well, if you want to check on the plane whether a Lie algebra consists of Hamiltonian vector field with any symplectic form. What you will have to do is to look for vector field for some form such that for every vector field you will have something like that. Okay. But since this is closed locally, at the beginning everything is local, this can be reduced to this locally, okay? Because if someone doesn't know, this the derivative can be written this, but this is closed, so this goes to 0, okay? And this thing tells you that the contraction with this of this is differential something, so the differential is 0, okay? And this is equal to 0. If this is 0, this means that the contraction with omega is closed, but locally there will be some Hamiltonian factor. This is a Poincaré lemma everyone knows. So at the very end, you have this. So if you have a Lie algebra vector field and you want to obtain your symplectic form related to it, okay? You have to find some symplectic form for which you have a solution. You have the vector fields, you have to find this, okay? Assistant of partial differential equations. As I said, good luck, okay? Because normally it's quite difficult. To sum it up, because it's quite technical, I did this theorem that sometimes simplifies the problem. I found a condition that it was easy to prove, to check out more or less, to see if this system had a solution, okay? And well, I tried to do it this way. It worked out that it took too much time. So what I did essentially here in all these theorems, okay, was I tried to check if this condition is satisfied. It's an easy condition, it's a necessary condition, but not sufficient. So if it does not apply, since this is unnecessary, I can delay several things. There was a second condition here to check whether to explain whether omega exists, and this one it was like solving a partial differential equation like this, more easier but like this. So what I did, if this doesn't work, I skip the Lie algebra, okay? And then to the second, I proved 2-3 theorems that give you how to construct the symplectic form out of the structure of the Lie algebra. Okay? And it worked. It was 3-4 results, and all the 28 classes can be classified. And you obtain this fun. Okay, here you have H, you have pi, F4, and there is nothing else. It's everything that it exists. So if you have a certain Lie algebra vector field, normally a dynamical system differential equation, and you the plane and you want to make it symplectic, Hamiltonian with respect to symplectic form, you check out the Lie algebra, go to the field. It's here, okay. There is a method, the theorem I saw you, it was constructive. It tells you how to construct it, and you will find it. If not, there is no. Life is new. And you can use another structures, okay? So here there are several examples you can use. There are Milne-Pin equations, Conter-Riccati equations, Kummer-Sparre equation, planar diffusion equation, integral system with trigonometric nonlinearities. This appears in classical systems. Harmonic oscillators, of course. Diffusion-Riccati systems that they appear for certain diffusion equations. Blah, 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 blah. There are lots of examples, okay? Wintermead did a lot, but I found that still. Wintermead used to say that every integral system is somehow related to this. I found this even for vacuums. What to do? I did just a couple of examples. You can generalize this. Okay? You can do more general classifications of fields, even non-antisymmetric. I'm doing the classification on R3. Okay, and something else. I managed to do several interesting things. I'm applying these stability systems on the plane, on the real line, classified, and it works out that it has both applications. So at the beginning, this is the first work reply we published in journal differential equations. No, it seems that people are quite interested. And this we obtained several citations. So this is everything. I hope that it was not too much technical, too much boring. So thank you very much for your attention. Thank you for the very interesting talk. Are there any questions?
Javier, the Riemann hypothesis can be formulated as saying that a very explicit vector field on a very explicit plane domain vanishes nowhere, has no zeros. And this, is there any hope that this formulation could be
No, sure not. I had no idea even of this form.
That's right.
It's fine. It would be nice to take a look at
very
it.
explicit vector field and a very explicit domain?
I have seen many equivalent forms of this conjugate about, for example, Hamiltonian operators having a certain spectrum, things like that. But this is new to me. I must confess it. I don't think so. I want it, but no.
When you said that it's that the existence of the Hamiltonian vector field is only a local result, you mean that it's only, I mean, there is a Hamiltonian, it's only determined up to a constant. You can add a constant.
Yeah, I mean, it's not, the fact is when you are looking for the symplectic form, the Hamiltonian is not a key. The existing, the explicit form of the Hamiltonian to you is not important, but it's not uniquely defined. No.
Right, but there is a question where this question of the additive constant is important, and that's when you have a group. If you start out with a group action manifold, you have the vector field.
Yeah, it's
by that. And then there's the question, if it's a symplectic manifold, then you have these so-called moment map, which maps you to the dual algebra, and it generates, so it tells you what the element is.
I mean,
but the moment map, I'm just going to finish this inside. The moment map is not necessarily equivariant, and that non-equivariance means that the Poisson bracket of the Hamiltonians is not actually equal the commutator of the vector fields, but it's not the so that's an important question. So do you know if there's an equivariant moment map?
First of all, I have several works about equivariant momentum maps. Normally, this adjoint equivariance is not necessary. There is another way to speak that condition. This is the first thing. The second thing about the Hamiltonian fact is that when I did this thing, I checked all the possibilities for the Hamiltonian functions. And I checked which is the Lie algebra of the vector fields we have for every Lie algebra, the possibilities. One is simple, not simple. For some of them, as you said, okay, the Lie algebra, for example, is L2, when they are simple, the momentum mapping will be equivariant. So you could apply it to that. But about momentum maps, recall that it is absolutely a theorem.
That's a theorem. That's not
it's a theorem, but everyone knows.
In your example, it's not all simple. Are they all?
No. I mean, for this case, I wrote this case, and I think for this case it's equivariant because it's L2, okay? But if you add a constant for any of these things, it's not anymore. You get another Lie algebra, if I remember, because I did that in this.
Well, it's always equivariant for a central extension. So if you can add one essential element, then it becomes equivariant. But without adding one, these are not all.
I mean, for SL2, this one is equivariant. I know because I make the calculations with the other.
There's no central
extension. For this one is equivariant because when you start making the brackets, let I have the chalk. With these things, and you have with R2, and you define SL2, and you define the momentum map, what you do, you momentum maps this thing. So what it happens with this thing is essentially that for every point in here, this momentum map will have the Hamiltonian. If you have x1, x2, x3, and they generate SL2. The thing is that you will have an action, local action of this sort here, okay? And the fundamental vector fields are the ones they appear in there, in the P2, for example. X1, it will have x1, x2 will be 2, X3 will be H3. And due to the symplectic structure, the way of describing this, it will be these, and these. So these things can be written as 1, 2, 3. Okay. And this thing with these three functions that they generate, they have a Lie algebra that is isomorphic to this. It will be at equivariant because indeed equivariant locally amounts to having a Lie algebra of this.
The definition.
Yeah, I mean, well, it's not the definition because it's local. I mean, if you define, for example, if you want to take, if you have SL2 and you define something that it will be some kind of discrete extension of this, you have another group that it is, for example, not connected. This condition is local, and the condition that not connected is a little bit more. It can happen that this is equivariant by means of, it's a matter of definition again.
For me, SL2 is simple, and simple groups don't have central extensions. Therefore, there's always up to a constant. The overall group, it's always with an equivariant.
Yeah, you know, the problem with us is that we are saying we have a little bit different definitions, and this makes things a little bit different. For me, equivariant means that this diagram is commutative. Okay, but this is something that it's not local. You can define the equivariance locally by means of a condition by saying that for every your Lie algebra, you can consider things in here with the Poisson brackets for everything. You will have a Hamiltonian function, and the mapping this into this, it will be such that this is something called local. This is for the momentum map. So this is a little bit different of this because this condition is local, this condition is not local. This condition implies this, but this condition does not imply in general this. But it implies when the group is connected. And what I wanted to tell you about the momentum map is that when you have this and the momentum map is not equivariant, the things does not work like that. There is another way of generalizing most of the things done by the momentum map. And the trick is dropping this, okay? And finding a new Lie group action. Normally, this new Lie group action is the formation of the coadjoint action by means of a cocycle. That the cocycle means how you put these functions and things like that. So, for example, Marsden-Weinstein theorem and many other stuff about the momentum map that they are usually done by means of the coadjoint joint invariance. I did it for actually it's written in a couple of words that people don't talk about it, but it can be done. I cannot tell you if this can be done for every stuff about the momentum map. So far, when I found this, I found something like this of the adjoint invariance. I found a way to delete it. So whether it is or not, I don't know. So for this thing works, this thing works. For several extensions, I truly tell you, I don't remember it right now.
The central extension is the same as one for the that is it.
Yeah, I was talking about a little bit different, you know, about this thing. And this can be done always.
Yes, because you have one.
Yeah, but I mean, yeah, the cocycle, yeah, it can be done. It can be done for every class, but it does not depend if it's a central extension or no. I mean, whatever
is the way you define central extension.
Okay, in that way, yeah, I agree. That's in that case. But again, it's a little bit a matter of saying explicitly what you mean. Okay, sorry. Maybe I answered your question or partially.
I think we agree. It's just for me,
Yeah,
it's obvious that for SL2 there's no central extension.
Yeah, no, it's not. It was about how. Anyway.
The classification of Lie algebra by vector fields you can apply to matrix Riccati equations.
Yeah,
And the sequence, yeah, it's exactly your project. Conformal. You shed light.
Okay, I mean, this was about projectives and things like that. In here, the only case it appears,
Well,
yeah, it works. I mean, the projective Riccati equations, they are defined by means of projective vector fields. Normally in here is,
exactly.
no, this one is this one. It's PMs. This is the projective one. So out of, if you do linear combinations of these vector fields, you will get the so-called projective Riccati equations, and they appear in many problems.
A conformal one.
It was done.
It was done, yeah,
It was done by you.
That was the.
I know, I learned.
The only thing we did is that, you know, it was a nice work. You have your superpositions. The problem again is that you have all the problems, and there are certain changes of variables that put these problems into your form. So in one term form, I don't remember. I don't know if it was Veronique still there. Many pages. Anyhow,
It was before learning was born.
it was okay. So I think it was for sure. Okay, the thing is, what I found is related to this thing, and you have certain vector, the algebras of vector. They are small algebraic, but if you try to find whether they are diffeomorphic or not, it's a problem. So sometimes you can skip it. You don't know it. So about the hierarchy, the Riccati hierarchy,
Yes.
we notice that there is 6. Well, you gave me 2 examples. I said, come on, I think that I have seen this commutation related before in your work. So I said it can be, maybe it's related to, it's more general, and I found how to generalize every member of the Riccati hierarchy up to a change of variable that is a high order differential equation can be mapped into projective one. So everything you did can be applied to this, and people were a little bit.
Yes, matrix.
Yeah.
Not vector.
Yeah,
Yes.
yes, matrix.
But there's a reason for it. Let me just say, and maybe you know, but there's a very relevant reference, which is the work that others did with Steve Schneider.
Yeah, I know.
Where they extended this. So we only looked at Riccati equations, the vector matrix Riccati equations, and also conformal type of Riccati equations. But there's a universality there. So what Steve Schneider and Winters did was to derive these superposition principles for a much more general field action. But the universality theorem tells you, if you're talking about a compact matter, what it is in all of these cases, you can embed it into a Grassmannian always. There's always a Grassmannian where you inherit the structure of the canonical bundle over the Grassmannian. And you just reconstruct everything that you did. It's a fancy way of saying you can go into higher dimensions where the equations are matrix Riccati equations plus a number of constraints. So every Lie type superposition system can be written as Riccati equations plus constraints.
Right, because I remember Schneider. Indeed, there are 2 works by Schneider and Winterleaf where there is a classification. There are 3 types because they are based on 3 theorems. These 3 theorems were related to not to general Lie algebras. It was with a particular type of Lie algebras of vector fields where you have some Lie algebras, some maximal idea, locally intransitive, something like that. So this result, because I discussed them with Winternet, there were 3 main cases. With these 3 main cases, they could put with a Grassmannian. I found several little mistakes in those papers, but it was just way stupid things. And it was everything over the complex. And as you said, you can do it as far as you put the vector fields in a canonical manner. And you could do this thing, as you said, to write all the superpositions. But as much as I remember, over the reals, these results does not apply. And there was a very important subcase that was not studied in there because you couldn't find the way to deal with it. It was a real one and it was related to maximally symmetric manifolds, I think it was. And in that case, the thing is that for particular cases, Snyder managed to do the same thing you did, that it was very weird, some of this. Winter asked me how to generalize this, and I found a way to did it with another case, but most of the cases I wasn't able to do. So when you said it is true, as far as I remember, it was complex. Yeah, complex. Complex, yeah. Yeah, for complex, it was a way, and it was, as you said, you put it up, I mean, and you found project.
First chapter.
Yeah, but as I told you,
Recalculate equations are leaf group action.
yeah, but as I told you, it's about a particular type, very general, but a particular type of algebras. This is one of the details. Here there are more. For example, there are cases that are not included in that, I think.
I think if you're dealing with non-compact cases and real forms, everything I said.
I mean, if you have these conditions, yeah, the thing is how general they are, these conditions. And I thought that they are pretty much general. And the other thing I did, but well, I didn't never finish. It was something of the kind. It is even more general that maybe Winter did, but I have some doubts. I never published it. And it was about the same idea. You have a Lie system, whatever. You don't need any restriction on the Lie algebra, and you put it up. As you said, you consider some differential equation that it is on a bigger Lie algebra, and it turned out that I was always, but well, certain conditions that seem to be quite general, to project onto the original one and to recover your Lie system like one of these. And it happened that I could do it, but I'm not sure. I mean, it's something that I did a lot ago. So, but it's the same spirit, but a little bit more general, I think. And by the way, the work by Snyder is very nice. And I had a pleasure to read it. Even if I remember Winter is going to him and asking maybe one detail and things like that. And Winter is yes, it's missing, but I must confess that.
But this universality is not, and that's an add-on.
No,
but the fact that it extended much more general feedback.
Yeah.
But the observation that everything can be brought to the cat is just universality. But it's only over the.
Yeah. Because indeed, when I talked to Winter, he told me several times that everything must be on the Riccati, complex and real, but I have no proof. And I think that it's.
Luckily for us, Javier will still be here for a couple of months.
I'm sorry, we're talking too much.
That's great. Thank you for today. Thank you for the pleasure.